Okay, so last time we saw, in our lecture, we saw that we could abbreviate the binomial probabilities. That's the probability of k of the number of successes in n tries being in an interval a, b by phi of a minus a half minus np over the square root of npq. Same mistake as I always do. I should have a b here. Minus phi of a plus a half, should be plus, should be minus, minus np over square root of npq. Alright. Now let's ask ourselves, well, what about if I want to look at the fraction? So let's say I want to say the probability that the fraction, so that is the number of success in n over n, so this is the fraction of success. Let's say I want to see if that's differ from, what do we expect it to be? Well, I expect it to be p, and so let me rewrite this slightly. So let's pick A, let's pick B equal to np plus a constant times square root of n, and A equal np minus a constant times square root of n. Then if we do that, then with rewriting this formula here, we can call the number of success minus np is differed from c square root of n and minus c square root of n. So I've just rewritten what was above. That's just rewriting that with this choice of A and B. And now if I rearrange this, I can rearrange this. I'm setting up what I started to talk about, which was the fraction of the number of successes. So now if I divide through by n, divide through everywhere by n, I get that the fraction of success, which is just the number of success divided by n, is different. So I'm dividing everything by n. So np divided by n is p. So the chance that this differs from p by more than a constant, now I've divided through this by n, so I have square root of n over n, which just leaves me with 1 over square root of n. So I get a square root of n here, and minus c times square root of n. So this is, of course, as n gets big, it says that this fraction, the chance that it's outside of the little interval, which is the size of the square root of n, 1 over the square root of n, is equal to, well, let's plug those choices in now. So the first choice is I put b in for np plus c square root of n. And so if I do that, the np's cancel, right? And I'm left with 1/2 plus c square root of n over square root of n square root of p cubed, which is the denominator down here. Right? And of course here, so let's just write it out one more time. Let's write out the other term. The other term is phi minus a half minus c square root of n over square root of n square root of p cubed. Now the square root of n in both of these cancel, and I'm left to discover that this is approximately c over square root of p cubed plus 1 over 2 square root of p cubed n, because when I wrote that the n's canceled, I really only meant they cancel from here and here. Of course, there's still one left there. And so I'm left with that minus phi minus c square root of p cubed minus 1 over 2 square root of p cubed. Okay, for large n, the circled terms don't matter at all. And we really see that in this ever-tightening interval, that we have some fixed probability of being in that interval. So if we take c bigger, if we make c very, very big, for big enough n, this will be a tiny little interval. And so we can make this probably as big as we want. So by making c large, then c over square root of n is less than epsilon for large, so this is small, for large n. And so what we discover is something which is often called the law of large numbers, which says the following. So the law of large numbers, as it's abbreviated, says that the probability that the fraction of success minus p is less than epsilon and greater than minus epsilon. This goes to 1 as n goes to infinity. Okay, so one way to see that is that these terms circled essentially go away, and then it says that, well, as n goes to infinity, this number gets smaller and smaller, and so the little window here, the fraction minus p that it's in with some fixed probability, this window collapses. And so by picking c bigger and bigger, so for instance if we pick c equal to epsilon square root of n, then this just becomes minus epsilon, this becomes epsilon. And then here, what we'll have is if we just solve for c, we'll have epsilon square root of n, and this will be epsilon square root of n. Now as n gets bigger, this goes off to, there's a minus there, no, there's a plus there, sorry. This goes off to plus infinity, and this goes off to minus infinity. And so what we're doing is we're integrating under the curve farther out. We're heading towards minus infinity in this direction, we're heading towards plus infinity here, and we're integrating under this curve. And as you know, when we integrate under the whole curve, the integral goes to 1. This integral here will go to 0 because it's going way out in this tail and just integrating under the tail. And this integral here will go to 1 because it's integrating all the mass. So the whole thing will go to 1. And this is called the law of large numbers.